Okay, so I just wasted 16 minutes recording a video where I had the audio muted on the host Zoom call. So I've been trying to do these videos through Zoom so the audio sounds better. But if my enthusiasm starts to flag in this one, I apologize. It's because I just recorded a 16-minute video that I had to delete. So, an electric field, this is a follow-up lesson from 7.2. Whereas we are dealing with electric forces, an electric field is a region where force is exerted on a charge. It's analogous to a gravitational field. It's a vector, so we can add them like we would forces. So we use the symbol epsilon for electric field, and that's KQ over R squared. Now, the force produced by an electric field, therefore, is epsilon Q. You're going to notice that this feels very analogous to G, which we looked at in 6.1. G m over r squared got us the acceleration due to gravity, and G is the gravitational field produced by a mass. In the same way, epsilon is the electric field produced by a charge. And so just like if you had mass times gravity, which will get you a force acting on the mass. In the same way, you can get epsilon times q, or you could write it the other way around so it looks analogous to the force of gravity. Then, in the same way, epsilon is a field. Oops. Epsilon is a field, so is g. They're both fields, and when you multiply by a charge, then the electric field produces a force. Now, before we get any further, a helpful way to visualize electric fields is by drawing some test charges. Test charges are always positive. So if we draw a test charge, we draw just a plus with a circle. And then we draw the field strength. The electric field can be used by drawing these lines radiating away from the charge. And the density of the field lines will give you a sense of the strength of the field. So it's not like there's some sort of formula like this many field lines equals the strength or anything like that. The idea is the more we draw them, the stronger the field. And since the field lines are all positive, they all repel each other. So that's why they're evenly distributed around the positive charge. Now, we could draw a negative charge, and the rules for the field lines for this is that the field lines radiate towards the charge. And so in the same way, if we want to emphasize a stronger field, we would just draw more field lines and they're evenly distributed. Well, if we have these two charges in some proximity to each other, the field lines just continue on naturally. Now they're going to repel each other, so you're going to get this bowing effect in the field lines. Kind of like when you have put iron filings next to a magnet and you see how the iron filings go along the magnetic field lines. In a similar way, we have electric field lines and they repel each other, and so we get this sort of like bowing effect. Now, you can also have a situation where if you have two positive charges, what happens? Because the field lines are going to radiate away from both charges, well, they repel each other. And so the field strength is actually additive. For example, there would be no field strength along that dotted line there for all the field lines that are emanating out of the charge here, the charges, and so on, just a bunch of field lines. Okay, so if we want to figure out the field strength, the point of these pictures is just to help you indicate direction and get a sense of the strength of the field if we draw more field lines. When drawing these diagrams, field lines always go away from positive charges and they go towards negative charges. And field strength is additive, which means the sum of the field strength at any location in space is the sum of all the charges around it, right? It's a vector. So if I want to know the field strength, I use red here. If I want to know what the field strength is right there, well, I know it's zero because the two charges are, say, they're of equal charge and equal distance apart, but the field lines from the one on the left are going to the right, and the field lines from the charge on the right are going left, and so they cancel each other out. Like the field strength cancels itself out here. Whereas if I consider this location here, the field lines from the first one are going to the right, and the field lines from the second one are going to the right, so they're going to add together. And actually, that's our first example. Now, this is going to look very similar to what we did in the 7.2, where we had 2-point charges, and we said, where can we put a charge so that the force acting on that charge is 0? So it's a similar setup, but in this case, we're saying, okay, we have two charges, Q1 and Q2. Q1 is positive, Q2 is negative, so all the field lines are moving to the right. And I've done some work here, but we want to know, what is the field strength at point P? What's the total field strength at P? And so we have the field lines all moving to the right, and so we can actually just add them together. It is this straightforward. So if we want to know the total field strength, I'll try to use a highlighter here so you can sort of see what I'm talking about. I did the calculations ahead of time this time, so hopefully that's helpful. Just pause it as we're going if I'm going too quickly through stuff, like always. And so if we want to know what the total field strength is, it's the field strength produced by the first charge, epsilon Q1, plus the field strength generated by the second charge, epsilon Q2. And if the diagram has served us, then we know the field lines are from both charges are moving to the right when we're considering location P between them. So I substitute the formulas in, so there you go. And then I noticed that there was a common factor of a Q from both terms, and so I factored that Q out. And then from there, I just subbed in my information that I was given. I had to do a little sub calculation here to figure out that if the distance is 45 and one of them is 0.27, then the other one has to be 0.18. That's trivial, whatever. I did some calculator work, and I came up with this value, roughly 3,000 newtons per coulomb. That's the field strength at point P. So that's like saying, what's the field strength of gravity at the Earth's surface is 9.8. What's the field strength at point P? It's going to be 3,000 newtons per coulomb. Now, you might have noticed when I was doing my calculations that there is no negative sign for the charge for the Q2. What was it, 3.3? The positive and negative values for the charges when dealing with fields, like fields and forces, we use the positive and negative just to figure out where the field lines are going. And then when we sub them into our formulas, we've already taken care of direction, so we don't sub in our positive and negatives. We just put in the magnitude of the charges. When we deal with energy, then we can keep the positive and negative charges in. But for now, we're going to just leave it as the positive and negative help us determine direction, and we just sub the magnitude of the values in. Now, part B says calculate the force, the electric force, if a charge 2 times 10 to the minus 12 were placed at point P. So if a charge is put there, what force does it experience? Well, since we calculated right here, we calculated the gravitational field strength, or not gravitational, the electric field strength there. So if we put a charge there, then it's going to be the electric field strength times that charge. And so we get a force of 6.4 times 10 to the minus 9 newtons. So that's like saying once we calculate Earth's gravitational field strength and we put a mass there, well, what's the force that it experiences? In the same way, once we calculate the field strength at a location and we put some charge there, then we'll figure out the force that acts on that charge. So it is analogous that way, which is pretty cool. Okay, for the next question, again, this one has a lot of symmetries as like we did from question 2 from 7.2. 2-point charges are arranged as shown. Q1 has this charge and Q2 has that charge. What is the field strength at the origin? So what's the field strength at the origin? Well, in the same way, we can start analyzing what the field lines are doing. We know that from Q1, the field lines are emanating out because it's positive, and from Q2, the field lines are emanating towards it. And it is summative, so you can move those vectors around and figure out right there And the resultant is going to be that one. That's the one we're going to figure out there. Well, these are at right angles to each other. One is down and one is to the right. So I can use Pythagorean theorem to figure out the magnitude of the force that's being experienced. So I sub them in, and since I recognize they're at right angles, I can use Pythagorean theorem. So I calculate the first electric field strength squared plus the electric fields, the second one squared, square rooted, right? Same thing we've been doing all course. But if as I distribute this 2 to all the terms, then I get a k squared q1 squared over r to the 4, k squared q2 squared over r to the 4. That means there's a common factor of a k squared and an r to the 4 squared from both terms. So I can factor that out and then move it out of the square root sign, and I get a k over r squared, which leaves just a q1 squared plus q2 squared, which makes my calculations way easier than what we were doing. So I just sub some values in, and then I get a field strength of 4.5 times 10 to the 7 newtons per coulomb. Now, how did I get the angle? Well, just like we were doing before, if right, like in previous chapters, we can say that if that's theta, then we're going down and to the right, so that's tan theta. So that's opposite epsilon 2 over epsilon 1. So tan inverse of epsilon 2 divided by epsilon 1. And then I sub the formulas in because I know there's going to be some canceling out that happens. And I'm just left with Q2 divided by Q1. So tan inverse of Q2 over Q1. And I punched that in my calculator and I got an angle of 27. So that means the field strength at the origin is 4.5 times 10 to the 7, which is a huge number, newtons per coulomb, down 27 degrees right. So there is the field strength at that location. Is there a part B for this one? Nope, that's it. Okay, so it has a lot of similar feel for what we're doing for uh, force from 7.2, but now we're talking about electric fields. What's the field strength at a location? And I'm going to skip over this page. I think when Mr. Campbell put this in, he was expecting to do the diagrams on this page. I'll double check that with him, but I think we're okay to leave it like this. And then for the next page, when we're talking about uniform electric fields, we'll talk about, they're called parallel plate problems. And so, when we have a point charge, field lines emanate out and they're not uniform, right? Uh, they have a certain density. They're closer together near the source, right? They're closer together there. But as we radiate out, like that circumference is so much greater, even though the number of field lines are the same, so the density is less, so it's not a uniform field. But if we consider a parallel plate problem, right? Here's a metal plate, and here's a metal plate, and then we have some wires hooked up to the ends of a battery. So here's a positive, here's a negative. And so we know the negative charges move, and so there's going to be a buildup of negative charges on this plate, which repel the negative charges on the top plate, which leaves a positive charge behind. And then what happens is because there's such a buildup, it's such a density of electric, like of the negative charges, the field lines end up being just uniform and parallel, right? Because they're all packed in there so tightly. Except for what you might have noticed right away that I was drawing that wrong because the field lines are supposed to emanate away from the positive charge and towards the negative charge. There you go. And so that's how we can generate uniform electric fields. Now there will be some bowing still at the ends, but we have a uniform field right through the middle. And we're going to take advantage of that in 7.4, talking about uniform electric fields and how we can use it. And it is still analogous to what we do with gravity. Like Earth's gravitational field, G, is when we say 9.8, that's assuming a uniform electric field, but the formula is actually G ME over RE squared. So as you move up, like up and down the away from the Earth, you're changing your R value. So you're actually changing uh, the gravitational field of the Earth. Like that value 9.8 is not a constant. We treat it like a constant, but it's not. And so, in order to do 7.4, we're going to consider parallel plate problems where there's uniform electric fields, and then we can still be really analogous to what we've been doing for how we've been treating gravity and um, and then we can use the things we've been doing with gravity with electric fields. Okay, last thing, cycle. We're going to update part of that page on cycle. So if we turn back a couple pages, there was one labeled this, and we had started the process. We said Fg was G m1 m2 over r squared. And we had noted, the only thing we had written down was when we introduced uh, gravitational field. We can divide by m to move down on the cycle here. Well, now we can add a parallel piece here. We have the electric force, which is K Q1 Q2 over R squared. And if we go down on the cycle and divide out a Q, we get epsilon. So you can see that there's this symmetry between the two cycles here, which is kind of neat. This is measured in newtons. This is measured in newtons per kilogram. This is measured in newtons. This is newtons per coulomb. So we're seeing all these symmetries. And the next part of the cycle will be moving across when we multiply by r. Well, if we multiply F, the force of gravity times the distance, we get gravitational potential energy. So we're going to get something similar when we multiply by a distance. So that's what we're introducing in 7.4. What happens if we move through a uniform electric field? What happens to our electric potential energy? So that's what we're going to be looking at in 7.4. And we're going to be filling in this cycle as we learn more topics. And I'm curious if anyone has any ideas what's going to be in this corner of this cycle. Okay, good luck on this homework. Hopefully the audio worked this time, or I'm going to be in a real bad mood because it's 11:33, and if I have to record this a second time or a third time, whew. Okay, good luck, and if you have any questions, be sure to email me. Hopefully I can get back to you if they're quick, and good luck.